Hi, my name is Omar, and I'll be presenting my AER1516 Final project. My project title is Motion Planning for Quadcopters Flying Through Narrow Gaps. And here is the agenda for the presentation. So the objective of the project is to essentially solve the motion planning problem for a quadcopter that has to fly through a series of narrow gaps. So imagine having a wall that has a series of openings as shown here. So for the quadcopter to be able to fly through that wall, it has to maintain a specific orientation as it flies through the openings. And that presents two main challenges. The first challenge is actually finding that specific configuration. So imagine just using a standard sampling-based method. The probability of finding that exact orientation could be very low. So we have to do something else. The other challenge is the fact that the quadcopter its x and y accelerations are coupled to its roll and pitch rotations. So that means that for example, for this case, the quadcopter has to approach the opening and exits the opening at a specific motion profile. And that motion profile is, in this case, is parabolic because you will have an acceleration in this direction. So for some of the related work, the configuration space for quadcopters lies in SE3. And solving the motion planning problem in SE3 could be exceptionally difficult. So instead, the differential flatness property of quadcopters was exploited. And this means essentially that the state or the configuration of the quadcopter can be expressed in x, y, z yaw, which is the flat output, and their derivatives. And there's a unique mapping between the flat output space and SE3. So we can solve the motion planning problem in the flat output space and convert that back to SE3 if needed. So Melliner and Kumar has used this approach to solve for optimal trajectories that minimizes the snap of the position. That essentially results in trajectories that are very smooth in the input space of the quadcopter, and this technique has proved to be very successful. Then Richter et al. Came along and they utilized the work done by Melliner and Kumar along with RT star to generate a motion planner for quadcopters. So RT star here is used to generate waypoints, ignoring the dynamics of the vehicle, and then these waypoints are used to generate the optimal trajectories. So the work done by Richter et al. is what's used in this project, and I build on this on their work. So now getting into our problem statement. So given that the centroids of the narrow gaps or the openings are known, so we're going to assume that these centroids of these openings are measured by some sensor. And also given that the configuration of the quadcopter is defined using its flat output, x, y, z, and their derivatives. And note that we're gonna ignore yaw to simplify the problem. So the objective is to solve for the optimal set of configurations that will form a trajectory that satisfies the dynamic constraints of the quadcopter and also minimizes the total distance traveled in the environment. So just a couple of assumptions. First, we're going to assume that all the narrow gaps are convex polygons, and that will help in simplifying the collision checks. Also, we're going to assume that all the edges of the gaps are planar, so all the edges of the opening lie on the same plane. And finally, we're going to assume that the quad rotor is modeled as a disk, and hence that's why we ignored the yaw in the configuration. So now getting into the methodology used in the project. So similar to the approach used by Richter, RT star is used to sample the space using a linear steer function. However, if the random sample lies within a certain box in 3D, defined around the centroid of the narrow gap, then instead of doing normal RT star, the set of parabolas that define motion through the centroid of that gap are sampled instead. And I'll go through the details of this process next slide. But essentially, once RT star is done, the path can be pruned to remove any lazy states, and then minimum snap trajectory optimization can be done to get the optimal smooth path. So this is the algorithm for the overall planner. So step one is to do RT star, which is this algorithm. which is just traditional RRT star, except for these two steps in which we sample this window. And then the best path is picked, followed by pruning, removing any lazy states, and then minimum snap trajectory optimization is done. So if the sample generated by our RRT star gets within the box defined around the narrow window, instead of doing a normal RRT star close to the narrow window, which will have a very low likelihood of finding the exact configuration that will make the quadcopter fit through the gap. Instead of doing that, we actually sample the set of parabolas that go through the centroid of the gap. And the reason why the motion profile is parabolic is because we're assuming that the quadcopter must maintain a specific pitch and roll as it's going through the gap. And since pitch and roll are tied to the x and y accelerations, then the resulting path is parabolic. So this is the algorithm for doing the parabolic sampling. So step one is to sample the acceleration in the y direction and the velocity in the x direction. And they are sampled from two permissible sets, which contain realistic values for accelerations and velocities. Then the motion profile is generated using this formula, and then it's checked for collision. If there is no collision, then two points or two nodes at the ends of the parabola are generated, and these nodes are the ones used to connect to the rest of the RRT star graph. And also note that all the planning here happens in the local frame of the gap to simplify the problem. And then once the planning is done, it's converted back to the global coordinate frame. So using this technique, there's a higher chance of actually finding an actual profile that will go through the gap, rather than just doing RRT star in such a narrow, tight area. So now getting into the minimum snap trajectory generation. There are two common approaches for solving this optimization problem. The first approach involves solving a constrained quadratic program in which the coefficients of the polynomial segments forming the trajectory are solved for. And essentially, we impose constraints at the endpoints to ensure that the derivatives are smooth. So I attempted this approach initially with a standard polynomial formulation, where the time t here lies within a specific range that's assigned based on the length of the segment. And I found this approach to be extremely unstable. So instead, I attempted to normalize the time in which I divide the time by the total time assigned to the segment. And this normalization helped to really stabilize the solution. And this formulation is actually the formulation I used for my experimentation. The other approach involves solving an unconstrained quadratic program in which instead of solving for the coefficients, we solve for the derivatives at the endpoint. And I attempted to essentially use this approach for my problem, and it proved to be stable, but it produced longer paths on average compared to this approach. So I used this approach instead. However, I should mention that I did not spend much time experimenting and optimizing this cost function, so this approach could be improved upon. So finally, this is the algorithm for generating the minimum snap trajectories. So essentially, we start by generating the trajectory from the original original path generated from RRT star. And if we encounter a collision, then we add a point along the straight line between the original points and keep repeating that until a maximum iteration is reached or a collision-free path is found. So for the experimental setup, I set up an environment with two walls. Each of the walls contain a couple of angled windows. So I set up two sets of experiments. The first set involved windows angled between 0 to 10 degrees. So that produced trajectories with mild curvature. And the second set involved windows angled between 10 to 20 degrees, which produced aggressive trajectories. I tested both in 2D and 3D. So in 2D, I had all the centroids of the windows on the same plane, and all the samples were sampled from that plane as well. However, in 3D, the window heights varied. And as a benchmark, I used RRT star with a polynomial steer function and with a stage cost that penalized the path length and the path curvature. Since this approach essentially produces a near optimal trajectories, it was a good way to compare the results against. So getting into the experimental results. So for all of these cases, I ran the algorithm for 100 iterations and calculated the average and standard deviation of the times and lengths produced. So a couple of key things to note. The first thing is that the average lengths produced by the mild curvature cases were always shorter than the lengths produced for the aggressive curvature. And that makes sense because for aggressive curvature, the quadcopter must maneuver a longer path in order for it to achieve the desired curvature at the window. And then the second item is that the method produced very close results compared to the benchmark, which is RRT star with the polynomial steer function. So if you compare the average lengths produced here and here to here and here, you'll see that they're very close, which means that even though the benchmark produces near optimal results, the algorithm was able to produce very, very similar results, although the algorithm does not guarantee optimality. And also the algorithm was almost twice as fast compared to the benchmark setup. And finally, one final item, the algorithm was able to actually cope with passing very close to the obstacle. So if you look here, for example, the algorithm had to actually put a lot of midpoints when solving for the minimum snap trajectory, and was able to do that and find an actual feasible path in a numerically stable way. So here are a couple of demonstration videos for the mild curvature case and the aggressive curvature case. I had some issues running the videos while recording, so instead I encourage you to click on the YouTube links and watch them. For controlling the quadcopter in the simulation, I used a model predictive controller with feed-forward linearization, and it achieved pretty good results. However, there is some overshoot, especially in the aggressive curvature case. However, this performance can be further improved if the controller is optimized. So now discussing a couple of points. The first point is optimality and completeness. So RRT star itself is resolution optimal and resolution complete. However, since we're adding the minimum snap trajectory step on top of RRT star, then the algorithm loses its guarantees for optimality and completeness. And a simple example of that is in this scenario here, the desired optimal path should look something like this. However, the algorithm will produce something like this path here because it's trying to follow the straight path, but have to meet some curvature at this end. But although the algorithm does not guarantee completeness and optimality, it still performed very well when compared to its benchmark RRT star with the polynomial steer function. The other item is computational complexity. So RRT star itself is order n log n. And on top of that, we have the lazy state contraction and minimum snap trajectory generation. However, these two steps can be assumed to have a minimal impact on the complexity as long as the number of nodes along the path generated from RRT star is moderate. So overall, we can say that the algorithm has an order of n log n. So to sum up, the approach presented in this project aims to solve the motion planning problem for a quadcopter flying through a series of narrow gaps. The key aspect of the approach is instead of doing RRT star sampling at the vicinity of the narrow gap, the set of all possible motion profiles going through the centroid of the gap is sampled instead, and that helps into improving the robustness of the solution. The approach has proved to be effective at producing smooth trajectories that can be tracked by the quadcopter, and has proved to perform similar results against its benchmark RRT star with a polynomial steer function. So some of the future work is optimizing the approach to run in real time. So I'd consider using C++ instead of Python for implementation. And the other approach, or the other item, is utilizing the method used by Richter for optimizing the time for each of the polynomial time segments. So right now, the time for each of the time segments is assigned arbitrarily, and this time can actually be optimized, and which can improve the performance of the algorithm. And finally, I'd consider generalizing the approach for non-convex and non-planar narrow gaps in order to make this approach more applicable for real-life scenarios. Thank you very much for listening, and if you have any questions for me, please don't hesitate to email me. Take care.